Good morning, Professor, and good morning, everyone. My name is Pratyusha Talapureddy, and my student ID is 11749152. I'm from University of North Texas. Today, I will be presenting our project on CNN-based classification using the CIFAR10 dataset. Overview of today's talk is Introduction to Neural Networks and Their Evolution, how CNN work and why they are effective. Understanding the CIFAR10 dataset and its challenges, building and training a CNN model, evaluating and improving model performance. Now going to next slide, neural networks. What are neural networks? Neural networks mimic the human brain consisting of interconnected neurons, layers in a network. There are three layers in network: input layer, hidden layer, and output layer. Input layer means receives raw data. Hidden layers extract meaningful patterns, and output layer produces the final classification. Activation functions ReLU and sigmoid introduce non-linearity, enabling the model to learn complex relationships. For example, image handwriting recognition, neural networks learn to recognize digits despite different writing styles. Now, evolution of neural networks. Early neural networks struggled with high dimensional data like images. Traditional fully connected networks require too many parameters, making them inefficient for image classification. Convolutional neural networks were introduced to handle images more efficiently. Now I'll ask some questions. Why CNNs? CNNs means it extracts spatial features automatically, unlike FCNs. Key innovations using convolutional layers to detect edges, shapes, and textures. Used in self-driving cars, medical imaging, and robotics. Now, what is CNN? It is convolutional neural networks. Convolutional layers extract features from the image. Pooling layers reduce the dimensionality while keeping important information. Activity functions add nonlinearity, that is ReLU, and fully connected layers make final classification decisions. The analogy from CNN is the first layer detects the edges, and the second layer detects eyes, ears, and whiskers, and the final layer recognizes it as a cat. Like it is the example for imagine recognizing a cat. Now, the next slide, dataset information. This is the CIFAR10 dataset. CIFAR10 is a benchmark dataset for image classification. The overview of dataset is it contains 60,000 images, which is 32 into 32 pixels RGB, and 10 categories. They are airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. And we have two types of data in the training data set and testing data set. In training data set, we will take 50,000 images, and test data set, we are taking 10,000 images. The challenges in this data set are images are small, like 32 by 32, making features extraction harder. And some classes have similar features, like example, cat versus dog. Next slide, CNN model implementation. Our CNN architecture consists of two convolutional layers. First layer is 32 filters, 5 by 5 kernel extract edges and shapes. And second layer is 64 filters, 5 by 5 kernel extracts more complex patterns. And pooling layers, max pooling 2 by 2, which reduces image size, improving efficiency. And third one is fully connected layers, flatten the data into a 1D vector, uses 1024 neutrons for classification. And fourth one is softmax activation function that converts outputs into class probabilities. Optimization and techniques user. It is ADAM optimizer, which is dynamically adjust learning rates and cross entropy loss, which measures the classification error. And next, training process. Training the CNN model. How the model will learn. Data preprocessing, batch training, and drop out the regulations. First, data preprocessing. First, we will normalize pixel values like 0 to 0 and 1 and apply one hot coding here. After that, batch training, we uses mini batches like size 50 for better learning and dropout regulation, which means prevents overfitting by randomly deactivating neurons during training. Next, evaluation. Model performance and evaluation. Here, accuracy is measured using test images, and the model correctly classifies objects 75 to 80% of the time. Accuracy graph is which shows how the model improves with training. The potential issues from this evaluation is overfitting, which means model performs well on training data, but not on test data. Need for data augmentation to make the model more robust. Next, uh, improving model performance. Uh, it is the conclusion. There are three key enhancements. Those are data augmentation, transfer learning, hyperpara tuning. Data augmentation means rotating, flipping, and zooming images to increase dataset diversity. And transfer learning, which means using pre-trained models like RESNet or VGG for better feature extraction. Now, hyperparameter tuning. Adjust learning rate, batch size, and number of layers to optimize performance. This is the conclusion. Achieve good accuracy on CIFAR 10. Performance can be improved with pre-training on larger datasets and fine-tuning and feature extraction, domain-specific data augmentation. Uh, CNN Excel in image classification task, fine-tuning CNN architecture. This is the PPT of my project. Thank you. Now I'll show the Python files. I created two Python files which named DLTFCNN CFOR 10 final project part V, 4 and 6. This is the fourth one. Here we can see that we are importing pandas library as pandas as PD and matplotlib.pyplot as PLT. Now we are setting path for data folder as putting file path as a string here like cifar underscore dir. Here we are setting path. Now we are loading the data by using unpickle function and now importing the pickle library. Here we are loading the data set. It is the data set. We are having 7 data sets in one directory. we named as the DIRs, and these all are dataset names. Here we are creating variables for the all the datasets. Now the batch data is all uh, dataset names. Now we will display several examples of single images using matplotlib. Like we are importing matplot library. Now importing numpy as np. Next we are reshaping the data set. Here it is the image which we are displaying single images by using these matplotlib. These are the images. Now supporting functions to rearrange the data, like we encode labels into one hot format by using one hot def one hot encode function. Here we are encoding the labels. Now we will set up image data, like make it ready to be fed into first convolutional layer. Here this is the code for setting up the image data. We are setting up images by using setup images function and next batch function. After this, we set up the image data and calling cifar helpers dot setup images. Here we are setting up the training images and labels and setting up testing images and labels. And we are now defining support functions to build, train, and test and test the CNN model. We are initializing here weights by using initialize weight function. Here we are initializing bias. Here we are creating convolutional network support by using this function. And here we are creating a ReLU activation function setup. And here we are creating pooling layers of 2 by 2. Now we are creating the setup of fully connected layers by using the function create fully connected layers and compute dot product plus bias. Phase 1 is build convolutional neural network. Here we are importing TensorFlow as TF. And now create placeholders for inputs and labels as X and Y true. Here we are creating a placeholder for the inputs data and a 2D array and a placeholder which can hold any number of rows. Here we are creating for a placeholder for another variable for y true. Here we are created for x. Now we are reshaping the input placeholder x. Not need to reshape the data here. Here create first convolutional, creating convolutional network. Uh, this is the variable one convolutional layer one outputs. This is the function create convolutional layer and compute dot product, and adding second convolutional layer here by using variable 2 convolutional layer 2 outputs by using the function creating convolutional layer and compute dot product. Here it is the pooling layer 2 outputs. Now creating fully connected layer and feeding the output. After that, this is the phase 2, which where we will train and test the CNN model on the dataset, which is the CIFAR 10 dataset. Here we are using the optimizer, like optimizer equal to tf dot train dot IAM optimizer learning rate 0.001. Now we are creating a CNN trainer equal to optimizer dot minimize cross entropy mean. Now we will initialize all the variables. The A is var, init equal to tf dot global variables initializer. Then we are entering the number of steps, which is 5,000. Now we are running TensorFlow session, like training a CNN. When we train the CNN, we will get the accuracy. The accuracy maximum is here, like 70%, 0.7064. This is the accuracy, and these are the steps. We are in this table. We can see that the accuracy and steps here. The highest accuracy for this training model is 71%. So this is the accuracy. We can see the graph here, accuracy versus stops. We are plotting the accuracy as y-axis and steps as x-axis, and we can see the graph here. This is the 70% accuracy. Mhm. Now we will look into the other part, which is the DLTF CNN CIFAR 10 final project part 6. Here we will import pandas as PD. Now we will set path for data folder as same like before. CIFAR directory CIFAR 10 data. Now we will load the data by using unpickle function and importing pickle library. Here also same, we will import the data set by using the variable dirs. Here we are setting variables for the data set. Here we are displaying data batch one dot keys. Then the key variables will be displayed. Now we will display several examples of single images using matplotlib. Uh, we use the matplot.pyplot as plt, and we will import numpy as np. And now same like before, we reshape the size. Here we are displaying different images of single images using matplotlib. Now we are supporting functions to arrange the data, encode the labels into one hot format. We are using one hot encode function for encoding labels into one hot format. And now we are setting up image data, make it ready uh, to be fed into first convolutional layer. Here we have user CIFAR helper and def function, classes CIFAR helper and init function. Now we are here another function def setup images and another function def next batch. After that, we set up image data by calling CIFAR helper setup dot setup images. Before we run these lines, we will set up the training images and the testing images, same as before. And now we define supporting functions to build, train, and test CNN models. Now initialize the weights, def initialize weights, and initialize bias like def initialize bias, and creating convolutional network setup, def create by using the create convolutional layer and compute dot product, and creating a ReLU activation function setup by using create ReLU layer and compute dot product plus b. And now we are creating pooling layers of 2 by 2, and after that creating the setup of fully connected layers by using the function create fully connected layer and compute dot product plus bias. Here you can see the code. Now we will start the phase one, which is the build convolutional neural network. Now we will import the TensorFlow as TF. Now we are creating placeholders for input and labels X and Y true. Uh, Here we are creating a placeholder for X variable as TF dot placeholder X equal to TF dot placeholder TF dot floor 32 shape none 32 3. And now creating a placeholder for another variable which is Y true equal to TF dot placeholder. And now we are reshaping the input placeholder X and after that we will create first convolutional layer and second like that. Here creating convolutional network by using a variable convolutional layer 1 outputs and creating convolutional layer and compute dot product. And after that we will adding a second convolutional layer. Like that we will add next third and next fully connected. Here you can see that the second convolutional layer, and now we can see that the third convolutional layer, and after that create fully connected layer. Here feeds the output. Now we can here we are feeding the output as fc dropout outputs equal to tf dot nn dot dropout. And now here we are seeing the phase 2. This is train and test CNN model on CIFAR 10 dataset. This is the train phase 2 for this dataset. Here also we'll use optimizer. Here we are using optimizer equal to tf dot train dot adam optimizer equal to learning underscore rate equal to 0.001. And now we are creating a CNN trainer equal to optimizer dot minimize cross entropy mean. And after that initializing all the variables. After that same we will add number of steps, and we will running a TensorFlow session. Here we are training a CNN. Now we can see the accuracy. Here the highest accuracy is 71.03. These are the steps. We can see here the table, and this is the accuracy. 7163 0.686765. For the 50 we will have get 66%. And now we are plotting the graph. Here we used the plot plt dot plot, and we took accuracy as y-axis and steps as x-axis. And here the plot is accuracy versus steps. This is the graph for the project. And this is the my IPYNB file. Now I'll explain my project report. Here part 1 is using TensorFlow directly in coding. Yes, I use a TensorFlow 1.xx version directly in coding. Yeah, I don't use Keras in coding. And the part 2 is a data set of images or audio files. Yeah, I have selected the satellite image classification dataset from Kaggle. This is the link which I downloaded the images from this link. And that this dataset contains 5631 JPG images, which are categorized into four classes. Those are cloudy, desert, green area, and water. And uh, cloudy are have 1500 images, and desert have 1131 images, and green area has 1500 images, and water contains 1500 images. And this dataset is valuable for training models to classify land types based on satellite imagery. Such a model can be beneficial for farmers and environmentalists and military applications, which enable better land assessment and decision making. These are the examples of images which I downloaded from the Kaggle. This is the cloudy data set, this is the desert data set, and this is the green area data set, images, and these are the water images. Here, part 3 is the obtaining CIFAR 10 data set. Uh, this is the screenshot of which I had this in my folder. This is the folder. These all are data sets which I downloaded from the Canvas module. There are 7 files which included 5 data batches and one batch and one meta file. We can see in the image. And now the step 1 is we have established SSH connection from the GCP and creating new folder CIFAR 10 data and setting path to CIFAR 10 data folder. This is the screenshot of SSH in browser. After that, by using, there is an upload file in this SSH in browser here. This is the upload file. When we click on the upload file in the SSH window, we will get one pop-up window like this. The upload file, we can choose files from that choose files option. It will enter into the file explorer. Then I chose CIFAR 10 data to upload the data into the cloud. Now all the files are transferred into root directory using cp command, which is used to copy, and I have copied all the files. Here you can see that I can copied all the files, and this is I uploaded all the data files which I downloaded from the Canvas module into the SSH browser. This is the transferring of all the modules into the SSH browser. This is the part 4, which is the building, training, and test CNN on CIFAR 10 dataset. Uh, what that means building on the previous CNN lectures on the NIST dataset. I developed functions to initialize weights and biases, and also I created different functions for constructing convolutional layers and apply ReLU activation function. And I built a CNN which has two convolutional layers. The first one convolutional layer has 3 by 3 filters with a 3 input channels and 32 output channels. This is the Jupyter file screenshot. It shows the test accuracy over the number of steps. We can clearly see that. And this is the comparing of convolutional neural network performance. And this image shows the result of CNN and MNIST dataset. It is the part for improving CNN performance. This screenshot uh, adjust a hold prop parameter during training and initially set 0.5 and reduce it to 0.3. This is the accuracy versus step plot graph. And part 7 is the project report. In this project, we implemented convolutional neural networks on the CIFAR 10 dataset, a widely benchmark in the computer vision community. The whole project overview is the goal of this project is to design and implement a CNN model and capable of achieving high accuracy on the CIFAR 10 dataset. Conclusion from this project is the lower initial accuracy of the model it given model 1 and several modifications were made to improve performance, and model 2 was developed based on the enhancements and through extensive training. This project provided valuable insights into tuning CNN hyperparameters to optimize performance. These are the references which I took from Kaggle and machine learning. That's it, Professor, and my friends. Thank you so much.